All right, folks, what we want to do today is we want to introduce a couple of quantitative analysis techniques, and these are techniques that we will use throughout the rest of the year in lab. So we're really going to focus on titrations. This is a lab technique that we'll use throughout the rest of the school year. We'll also look at some gravimetric analysis and also do an example on combustion analysis. So whenever we talk about a titration, what we're doing is we're looking at using a burette to add a titrant to an analyte. So what this means is the analyte might have an unknown concentration, and we're trying to determine that concentration exactly. So we can add a titrant, which it could be an acid or could be a base. It depends on what the titration is. But if we're going to add an acid to a base, if we don't know the concentration of the base, that is our analyte, and if we're adding the acid to this base, this is our titrant. But we're going to figure out the unknown concentration. And what we're really going to focus on is reaching that equivalence point. And the equivalence point for us is the point at which chemically equivalent quantities of reactants have been mixed together. So what does that mean for us? Well, that just means at this point in time, since we're only considering titrating strong acids with strong bases, which means that they're strong electrolytes and they're dissociating completely, this just means that our moles of H plus is equal to our moles of OH minus. So whenever we first start out, we may use indicators where we can see color changes, but once we get into this class and lab a lot more, we're going to start to use pH probes so we can monitor the progress of our reaction more closely. You can also use gravimetric analysis, and this is whenever you have an analyte that changes physical state or is separated out. So you could think about a precipitation reaction. If you can figure out the concentration of an ion or maybe the initial amount of metal that's present based off of what is precipitating out of your reaction. And finally, we'll look at combustion reactions. So remember, for us, combustion reactions, we're looking at combusting hydrocarbon, so something like CXHY plus O2 yields CO2 plus H2O. And the way this should work is we should have X numbers of carbon dioxides and Y over 2 numbers of waters. So let's go ahead and try a few examples. So whenever we look at gravimetric analysis, this is based on a measurement of mass. This is really an accurate method, but it's only really good if your reaction goes to 100%. If it doesn't go 100% and you don't really have a way of knowing at this level how much is unreacted, so you have to know the mass that you're putting in and then be able to accurately measure the mass that you're getting out to form the precipitate. If you can't do this, this method falls apart pretty quickly, but it's good because you're able to use mass conversions to moles, use mole to mole ratios, and you're able to calculate the amount of product, or if you're interested, the amount of reactant that's present. What I want to do is I want to look at an example of a simple titration. So in this particular example, we reached the endpoint of a titration, and we have a 50 milliliter sample of aqueous HCl, so hydrochloric acid, and this was reached by adding 35.23 milliliters of sodium hydroxide. Write a reaction and determine the molarity of HCl. So what you want to do is you want to think about, okay, well, I have HCl plus sodium hydroxide. And whenever this reacts, we'll end up with water plus aqueous sodium chloride. In this case, it's already balanced. What you do have to watch for is if you have a polyprotic acid, so meaning there's more than one hydrogen that could possibly dissociate, or if you have more than one hydroxide. So for example, this would be if you had something like barium hydroxide, where there's two hydroxides. Then you'd have to be careful going through and balancing and keeping all track of your moles. Okay, so now we have a balanced reaction, so let's go ahead and determine the molarity of HCl. So again, what we're assuming is we've reached that equivalence point and that the moles of H plus is equal to the moles of OH minus. Well, if we're trying to find the molarity of HCl, so we're trying to find the concentration of HCl, well, the molarity is equal to the moles of HCl over the volume of HCl. So the way that we'll go about solving this reaction is we know the volume and the concentration of sodium hydroxide. So since we know the volume and the concentration of the sodium hydroxide, we can find the moles. So for sodium hydroxide, we know the concentration is 0.250 molar. We know the volume is 35.23 milliliters, which we'll have to convert to liters. So that means we can find the moles. So we can do this by saying, okay, we know that molarity is equal to moles over volume. So we're rearranging for our moles. We'll have moles is equal to molarity times volume. Plugging in for the sodium hydroxide, we have 0.250 molar times the volume, which we need to convert to liters. So it would be 0.03523. There's the liters right there. Once we plug this in, we'll find out that the moles is equal to 0.00881 moles. So again, since we're considering the equivalence point, our moles of H plus is equal to our moles of OH minus. And again, we started out with the concentration of NaOH, but since this is a strong electrolyte, we know that it will dissociate into sodium ions and hydroxide ions. So this number of moles corresponds to both sodium and hydroxide. So now we know the moles of H plus, okay, which we'll think about that as the moles of HCl. We also know that volume of HCl, which is 50 milliliters. So what we can do is we can plug in our 0.00881 moles, divide by the volume, which is 0.05000 liters. And once we plug that into our calculator, let's see what we get. We end up finding that the concentration of HCl for this titration is 0.176 molar. Okay, so again, the key points that you really want to focus on whenever you're solving these problems is what happens if you have polyprotic acids or multiple hydroxides, because you'll have to use a ratio between your acid and your base. So the last example that I want to look at is a combustion analysis. So here we are given that we know the mass of a sample of polystyrene, and it's a polymer that's composed of only carbon and hydrogen, and it produced 0.00726 grams of CO2 and 0.00148 grams of H2O in a combustion reaction. So we need to figure out what the empirical formula is. So again, recall that generic reaction is we have CX HY, where we have X numbers of carbons, Y number of hydrogens. We're going to use this combustion reaction. We'll have an excess of oxygen. We'll form X moles of CO2 plus, let's see, we'll have Y over 2 moles of H2O. So now what we can do is we are trying to compare how much carbon and how much hydrogen came from our initial hydrocarbon. So we can start with our initial mass of CO2. And from here we can find the moles using the molecular weight. And that molecular weight is 44.01 grams of CO2. And then what's the mole ratio of carbon to CO2? Well, we know it's for every 1 mole of CO2, there's 1 mole of carbon. And we can plug this in and we'll find out that we got 1.65 times 10 to the negative 4th moles of carbon, which had to come from that initial hydrocarbon. We can also do a similar process for the water. So we start with 0.00148 grams of water. we can convert that to moles. So for every 1 mole of H2O, it's 18.02 grams of water. But now the mole-to-mole ratio is, for every 1 mole of H2O, there are 2 moles of hydrogen. Whenever we plug this in, we get 1.64 times 10 to the -4th moles of hydrogen. So many times people will convert these moles into grams, but since we're asked to find what the empirical formula is, and we know that we go from percent to mass and then mass to moles, we're comparing mole-to-mole ratios. So we can just compare the moles of carbon to the moles of hydrogen, and that will tell us the ratio in which carbon and hydrogen combine. So in this case, they're both essentially the same number. There's probably a little bit of error from rounding off the molecular weights or truncating the result from the calculator. But whenever we go through and divide, we end up getting a 1-to-1 ratio. So the empirical formula for this polystyrene is CH. So sometimes it comes out to be fairly simple like this, and other times there's more components which can make it slightly more challenging. But you really want to focus on the carbons and the hydrogens in this case. So that concludes our initial introduction to quantitative analysis, but you really want to focus on titrations as we start to go forward.